Fourier analysis, or some analog of Fourier analysis on the group SL2R. And we thought, well, after some debate, we thought we'd actually begin with just a classical discussion, because there are some minor points that even those who are familiar with analysis might find a little strange when it comes to SL2R. So I'll try to cover those points today. So I'll start off just with periodic functions. And I'll generalize things very slightly, just to, well, again, say the slightly unorthodox notation maybe. So let L be a positive number. That's going to be the period of the functions I'm looking at. So I have a smooth function f, and, oh, yeah, there's a typo. It's a smooth function of period L. So it just means it repeats every L units in the real line. Then it can be expressed as a moment as a Fourier series, a convergent Fourier series, in fact. And we want to obtain a formula for the coefficients. And so if this expression is valid, then I can obtain the Fourier coefficients by multiplying by one of the terms and integrating against that, and everything drops out. When I do that, everything drops out except one of the terms. And so I have a formula for the coefficients, which looks like this. The nth Fourier coefficient of the function whoops, yeah, it has that formula there. Let's see. Yep, that's right. That's right. So this is a function. Now, the slightly unorthodox feature is I don't take the Fourier coefficients indexed by L, but I take them indexed by n over L, and that's because the expression here is x over L, really. I mean, excuse me, the index here is k over L. That's really the way it works out, and so I prefer to index it like that. There's a reason for doing that won't appear, but in the final version of the notes, I think it will appear. Okay, and so this is the Fourier transform. So this is a function. The index of the Fourier series is then a function on the fractions which have denominators a multiple of L, a divisor of L. Okay. And then I've assumed my function to be smooth. So in particular, it's continuous, and then when you get a constant bound on the Fourier coefficients, that's independently of n. So the Fourier coefficients will have a fixed bound. There are some finer results, something called the Riemann-Lebesgue and so on. I don't need that. What I need is something much simpler. If I, well, first of all, I calculate a few Fourier coefficients. If I actually take one of the periodic functions itself, one of the basic functions, then I just get 1 or 0, so that works out nicely. If I multiply my function by this, then I do a shift on the Fourier coefficients. And the most important thing is if I take the derivative and I take that Fourier transform, then just integration, well, just the derivative inside the integral gives me this fact that the Fourier transform in these terms of the derivative is equal to 2 pi I n divided by L times the Fourier transform of the original function. So the whole point of Fourier transformation is that it really transforms differentiation on the original function into multiplication on the transform. And if I take the kth derivative, then I just multiply by k here. So differential equations get translated into algebraic equations. That's really the whole point of the Fourier transform. And so the Fourier coefficients decrease more rapidly than any negative power of the absolute value of n as n goes to infinity. So the Fourier transform lies in what at least one student, one among you called the Schwartz space of z quotient L. Those are the functions. So z quotient L is a discrete set, so I just have these functions which are rapidly decreasing as a function of the index. Okay, are there any questions? So this has all been implicit in things we've said so far. Conversely, if I take a function in the Schwartz space of Z mod L, then I define its Fourier series to be this. And because f lies in the Schwartz space of Z mod L, this converges uniformly on R. And so we have the following thing. We have C infinity of R quotient Z times L goes to the Schwartz space of Z over L. And this is f goes to f hat. And then I have a map back again, which I haven't given a name to, but I'll just call it f goes to something. I don't know. It doesn't have a name, but it's the Fourier series. Okay, so I have these two maps. I have this map going this way, associated to a function as a set of its Fourier coefficients. I have a map going back the other way. If I take the Fourier coefficients, I assemble the series, and that gives me a continuous, in fact, a smooth function on this. And these maps are almost, but not quite. Well, these maths are actually inverse to one another, the way I've expressed it. Okay, and so what happens is the basic statement, the basic theorem of Fourier series is if f is a smooth function, then the Fourier series converges to f. Okay, I'll give a very quick proof of that. There are different proofs, but in this situation, everything smooth and nice is no. Ordinarily, what you prove is that if the function is piecewise C1, then the Fourier series actually converges to it. And there are some technicalities that requires, but in this case, it's much simpler. It doesn't look simpler, but there's no technicalities. It's just a bunch of equations. I won't give the details of this, but anyway, this proves basically that everything works out all right. And the key fact is that if I take my function, I evaluate f of 0 and I subtract f of x, and then I subtract and I divide, that's divisible by x, so to speak, as a thing. Of course, x is not periodic, so I make this. Eta is this function here. This also, eta is equal to 1 at 0, so both the functions here are differentiable. This function and this function are both differentiable and equal to 0 at 0, so I can divide one by the other, and it's a 0 over 1, so I can divide one by other. That's still a smooth function. So I'll leave that for later. Anyway, that's the word. So the final conclusion is that the Fourier transform on periodic functions is an isomorphism of the periodic functions with period L, smooth periodic functions with the Schwartz space of Z mod L. Okay, and that's very simple. It's basically algebraic. There's a little calculus and no serious analysis. If I calculate the L2 norm of my function and replace it by the convergence series, write this all out, then you get an obvious equality that f squared is equal to the sum of the squares of the Fourier coefficients. And so what this means by sort of general analysis results is I can extend my isomorphism of the smooth functions with this. I can extend that to a function, an isomorphism of the two L2 spaces. Okay, are there any questions? This should all be at least vaguely familiar to you, but I'm just racing through to give you a reminder what things look like. As I say, the notation is slightly different.
I mean, the last line would be C infinity. I want C with L2. No, L2 in both cases.
L2 in both cases.
So that is same as L2.
Well, I've defined my L2 norm here. My L2 norm of a function of a periodic function is given by this integral, and the L2 norm here is just the sum of the coefficients. Hello? This is the period. This is the fact that it's periodic of period L means that it's a function on R modulo the multiples of L. Okay. And this division by L means it's a function of the fractions of L whose denominators are divisors of L. Okay, so we have two. So the Fourier theory gives you two isomorphisms. I just want to say that it's not, so in general, if you want to show that one L2 space is isomorphic to another, there's some hard analysis to be done, but in this case, going through the smooth functions in this way, it's rather simple. Okay, so there are other ways to do this. Analysts probably prefer, real analysts probably prefer something a little different, but this is Schwartz's way of doing it. It's very nice. Okay, now, there's something which we haven't introduced, and frankly, we're not going to introduce. These spaces, so L2, for example, is a Hilbert space, and it's complete with respect to an L2 norm and so on and so on. There are lots of other different kinds of topological vector spaces with different notions of convergence. We're going to try to dodge that question as much as we can. We don't want to discuss convergence and continuity on these funny spaces. The technicalities they're pretty simple, but there's just lots of them. But still, it's useful to know that these are topological vector spaces. They have a notion of convergence. And the Fourier transform is a topological isomorphism. So these spaces, the C infinity functions, the Schwartz space, they're isomorphic as topological vector spaces. Any notion you introduce of convergence in one implies convergence in the other. This space is pretty simple. The Schwartz space of Z, it's just pretty simple. It's a very discrete space, infinite dimensional nice basis and so on. So the topology on that is rather simple. So these are topological vector space isomorphisms. And what this means is that they're topological, and here's the important part, their topological continuous linear duals are also isomorphic. Now, the topological linear dual on this space, on the Schwartz space of Z mod L, so I have a function which is rapidly decreasing on a discrete set. And the continuous dual of that has some topology I won't introduce, but the continuous dual of that are just functions which are of moderate growth. So if I have a function of moderate growth and I have a function of rapid decrease, I can multiply the two and then integrate them. So I should write that down because I didn't do that on the slide. So if f is a member of the Schwartz space of Z mod L, and capital F is a member of something, I'll call it mg. It's very bad notation, but I'll call it D. So mg is moderate growth. So let me remind you what this means. This means O of 1 over absolute value of n to the k as n goes to infinity and all k. And this means O of absolute value of n to the m, say, or capital N, for some n. Okay. So if I multiply these two, then, well, this is of moderate growth in 1 power of n, and this is rapidly decreasing in all powers of k. So if I multiply these two, this is still rapidly decreasing, and I can integrate it. So I have a pairing ff equals sum of fn times fn. Okay, so that's the duality between these two spaces. So this Schwartz space, so the whole, in a sense, the whole point of the Fourier transform is replaces this somewhat complicated C infinity space by an extremely simple Schwartz space in that, and you get this notion of the continuous dual. Now, on this space, the C infinity, the continuous linear functions in this space are called distributions, and in fact of period L because of the period. And so this is a somewhat complicated space, but on the other hand, we have it's isomorphic to this very simple space of moderate growth things. And now every continuous function f of period L can be considered a distribution through integration. In other words, if it's rapidly decreasing, then of course it's of moderate growth. And but there are other distributions. So automatically I get a whole bunch of distributions just by embedding the C infinity functions themselves. But there are other distributions, such as, for example, the Dirac delta, which is more typical of the ones we're going to be looking at. The Dirac delta is just the linear functional on smooth functions, which evaluates a function at a point. Okay.
Is it all the element of the dual of this Schwartz space is can be expressed in those forms? I mean,
It's moderate growth, yes. It's easy that if I actually told you what the topology was, you'd see immediately that any continuous linear dual functional on this space is just a discrete function of moderate growth. The topology somehow involves this, guarantees that. Okay? So it's a pretty simple space. So as I say, the purpose, so from one standpoint, the whole point of the Fourier series is just to look at distributions in a sense of, that's really the most important thing about the Fourier expansion, although maybe your bosses don't tell you that, but the most important thing is to get this nice space which is equivalent to the distributions. So you get a very algebraic description of what the distributions are, which is very nice. Okay. So for example, the Dirac delta itself, if you evaluate it, it has Fourier transform, I don't say actually, it's 1 over L. I think I say it later. Okay, and now there's one fantastic fact about distributions, which is that, first of all, you start off with a very simple inequality. If I take a smooth function and I consider it as a distribution, and then I take its derivative, which is still a smooth function of period L, I can integrate that against a function f. You write it out like this, and then if you integrate by parts using periodicity, you get this expression over here. So I can interchange the prime and the two different functions, but I get the change because there's a minus sign in integration by parts. And so the pairing of f prime with f is equal to the pairing of f with f prime and a minus sign in front of it. Now, this equation is basically an equation of distributions. It just says if I pair this with this, I get the pairing of this with this. And so I can define the derivative of a distribution by this property that phi prime paired with f. Remember, distributions are defined by what their pairing is with smooth functions. So phi prime paired with f is by definition equal to minus phi of f prime. And that's consistent with the usual notion of derivation on the smooth functions themselves, in fact on C1 functions. And so the amazing fact about distributions that makes them so incredibly useful is that every distribution has a derivative, and that's also a distribution. Now you can see that in terms of the Fourier transform, because taking the derivatives on the distribution side means multiplying by something on the Fourier series side. And you can, if I have something of moderate growth and I multiply it by a power of polynomial in n, then I still get something of moderate growth. So you can see that explicitly on the Fourier series side also. Are there any questions? What about?
Integration by parts, there should be boundary term.
Yeah, the boundary term vanishes because of the periodicity. In other words, the boundary term has something evaluated at L and something evaluated at 0, but these functions are periodic, so this minus this is 0. Okay, that's exactly the reason things work out. Okay. Any other?
Your Fourier transform depends on L. It's not independent.
On L?
Yes.
Absolutely. There's a reason for doing that, which is I say you won't see, but then I've done it just so as not to confuse you when you look at the final version. I'll say something about why I've done that, but that's right, I'm depending on L. Okay, so as I say, every distribution has a derivative, and that's actually a fantastic fact. Now, the exponential functions, the things I integrate against to get the Fourier series, those are smooth functions, and so I can evaluate a distribution on those, and so I can just formally take the Fourier transform of a distribution in the same way. And again, as you see here, I get these moderate growth things. That works out that way. And formally, the definition can be like this. If I take, it turns out if you verify some equation, phi hat paired with f is equal to phi paired with f hat. So again, just like I define distributions, I can define it in terms of a pairing. Phi hat paired with f is equal to phi paired with f hat. Before I had phi prime paired with f was minus phi paired with f prime. And well, then the Fourier, so I have the fact that this dual is given by polynomial growth, and that's actually the Fourier transform gives an isomorphism of the space of distributions on R of period L with the space of functions of polynomial growth. So for example, the Fourier transform of the Dirac delta itself is the constant function 1 over L. And one of the main points of defining the distributions, we won't see that, I don't think. Well, we might or we might not. We're thinking about it. One of the main points of defining distributions is to somehow generate solutions of differential equations which are not functions. And so using non-differentiability in a very algebraic way. So sort of using distributions kind of turns a lot of analysis into algebra, which is a good idea. I promise, I promise. Okay. So are there any questions about periodic functions? Mostly this is a review, I'm pretty sure. But yeah, yeah.
You said the space of distributions is the linear dual of the Schwartz space?
Yeah, well, it will be, for R, it will be, no, I'll explain something about that in just a moment again, but for periodic functions, the space of distribution, there are all kinds of different notions of distributions. And one is distributions of period L, and the distributions of period L are just simply the continuous linear, things in the continuous linear dual of periodic smooth functions. Okay. But there are lots of different notions of distribution. It depends on which functions, like you have distributions on manifolds. So these are distributions on the circle, for example. Okay. So now I want to make things mildly more complicated. I want to look at the group R itself, the additive group. And in this case, I'm going to look mostly at the Schwartz space of R, which is written S of R. And S of R is very simple to describe. R is not compact, so it's much more complicated than the circle. S of R is the space of all smooth functions on R, all of whose derivatives vanish more rapidly than any inverse power of the absolute value of x. So basically, a function, the typical Schwartz space are the Gaussian integrals, or Gaussian functions, which look like this. Okay. They include also, though, things of compact support, for example. And if f is in the Schwartz space, the whole purpose for introducing the Schwartz space is you can apply Fourier transforms to those. So if I take, so the Schwartz space for R plays the same role as all C infinity functions, which are periodic. If f is in S of R, then its Fourier transform is given by an integral instead of a sum. That's a natural thing to do. And the point is that this is again lies in the Schwartz space. That's an amazing and wonderful fact. And the reason for this is, well, it's the same sort of equation we had before. If I take the Fourier transform of the derivative, it's equivalent to multiplication. So again, taking the Fourier transform changes derivation into multiplication by a polynomial. So if I multiply by some constant coefficient differential operator, I'll get that corresponds to a polynomial acting on the Fourier transform. And in particular, this is bounded. Again, the same reason as before. This is going to be a bounded function, and so this will be a bounded function. So in the end, you get that f can be divisible. So this means that polynomials times f are bounded, and that means that f decreases rapidly infinity. And the fact that it's smooth as well, you just take the derivative and you get something nice. Okay. And so the inverse Fourier transform is given by an integral that looks very much like the Fourier transform, but it's just got a plus instead of a minus. That matches with what we did for series. An equivalent way to say that is if I apply the Fourier transform twice, I take f of x to f minus x. Okay. This is somewhat, it's not actually more subtle, it's less intuitive than the theory of Fourier series. I'm going to very, very quickly sketch two proofs, ridiculously quickly sketch two proofs. The first one involves the following fact. The Fourier transform of e to the minus pi x squared is just e to the minus pi y squared. So I have this duality. The short space maps into itself under Fourier transform, and there are, in fact, functions which are just taken into themselves, which is very nice. It's part of a much larger theory of Hermite polynomials, in fact, which plays a role in the theory of quadratic forms and also in the zeta function. Anyway, this is a lemma which you can make the calculation yourself. It just depends on knowing some integrals. To prove the theorem, you have to show that the f hat x is f minus x. It turns out that you can replace f by a shift or something, and you might as well take x equals 0. The Fourier transform takes, if I multiply x times the short space, then it's easy enough to see that that takes something into a derivative, and so it takes xs to the quotient of s by, the image, wish I could write that out, image of s by d. In other words, multiplication by x. So I know already that taking derivative corresponds to multiplication by something times x, and it's easy enough to see also that multiplication by x takes has Fourier transform, which I get by taking a different derivative, and so it takes xs into the image of s of dd. Oh, it's ddx. This is ddx. This is all done rapidly. Okay, and then back to x of s. And so what the theorem means is that, so what I get in the end, and this is the important part, the Fourier transform gives me a map from s quotient xs to itself when I take the double Fourier transform. And this identity here, that this is the inverse map, means that this is the identity map on this quotient space. And you just have to check what the constant is, and if you use this, and you can see the constant has to be 1. This is Laurent Schwartz's proof, and to those who are used to more complicated proofs, it seems ridiculously simple and a little twisty, but it's actually beautiful. It's the only proof. All other proofs are worthless. But it takes a while to convince yourself of that, especially with all the typos. Okay, there's another way to see it, which is also rather elegant, actually, and it's the one I teach engineers. And that's equally nice, but it's a little more technical. You can see it by, and this is why I introduced the L in the periodicity, is because if I take a Schwartz function, which is rapidly decreasing, then it's really the limit. I can take if I take a function of period L, then somehow if I get L bit bigger and bigger, in some sense I'm approaching the Schwartz function, a given Schwartz function. And I have to chop it off and then make it periodic, something like that. And on the other hand, you sort of fiddle on, so you can sort of see this, in fact, by looking at functions of period L. So using the same theorem about the inverse Fourier transform of period L, and then let L go to infinity. There's some nice pictures that go with this, but I don't have access to them here. So I'll just mention that there are two nice proofs, but the first one is for algebraic analysis. It's by far the best. Okay. And dual to S of R, the Schwartz space is a space of tempered distributions. Now, a distribution without the word tempered in it on R is just so if I look at the functions of compact support, the smooth functions of compact support on R, that's a topological vector space. It's a little bit complicated, which is why I haven't introduced it. The topology is a little bit complicated. But anyway, that's a topological vector space. That dual is called the space of distributions. But now I'm looking only at distributions which extend, so and this space is included in this one. Some distributions will extend to being distributions on the Schwartz space, and those are the tempered distributions. So being tempered is a strong restriction on a distribution. It's easy enough to construct lots of distributions which are not tempered, but we're interested only in the tempered ones. Among the tempered distributions, for example, are functions of polynomial growth on R, because I just integrate and everything works out right. And these also have Fourier transform. This is the same formula as I had before for periodic functions, and it works just as well here. I defined phi hat as a distribution. Its pairing with a Schwartz function f is equal to phi paired with the Fourier transform of f. And that works out just as well for this as it did for the Fourier series. So, and again, I can define derivative. I didn't say that. The notes are a little bit incomplete. Again, I can apply the same formula as I had before. If I can define the derivative of a distribution exactly as I did before. Phi prime of f is equal to minus phi f prime. And again, this agrees with the usual, by integration by parts, this agrees with the usual definition of a derivative of a smooth function. So again, we're in the same world in a sense. I have a notion of Schwartz functions to replace C infinity periodic functions, but for distributions it's the same. I can take the distribution, I can take the derivative of any distribution, I can take its Fourier transform. And again, the main use for these things is in solving differential equations. We'll see some examples on SL2R later on. Okay, now the third part of my talk, I'm just zipping right along here, is the multiplicative group. So let's see. If I take the exponential function, I can map the additive reals onto the multiplicative positive numbers. So these two groups are isomorphic. Now, the function 1 over x here corresponds to the function 1 over log x here. And so if I have something which is of polynomial decrease here, it becomes of logarithmic decrease here. So, but now the notation is a little, it's not quite fixed. There's some variations in notation. So in this course, I think this is consistent with what my colleagues are going to do. I'm pretty sure, actually. I'm going to define the Schwartz space of the positive reals to be those functions which are of logarithmic decrease at infinity and 0. So that's what I do here. So the multiplicative group of positive reals is isomorphic to R by means of an exponential map and a logarithmic map going back the other way. I define, this is a kind of Schwartz space. It's the Schwartz space. It inherits from the Schwartz space and the additive reals, but the condition of polynomial decrease changes to the polynomial type OH there, the polynomial decrease in the logarithmic decrease. And there's another feature, which is that d dx here becomes x d dx here. So this is an additive. This commutes with translation. This is an operator which commutes with additive translation. And this is an operator which commutes with multiplicative translation. Okay. And so my condition on the Schwartz space is that dn of f equals O of 1 over log nx as x goes to infinity and x goes to 0. And this should be an absolute value, right? Okay, so this is, but the notation is a little funny because I write this with a C instead of an S. And there's a reason for doing that, and that's my own idiosyncratic. I haven't really sold this idea, but there is a reason for doing this. This is where the analysts, even in my field, where the analysts divide into two groups, those who think it's a useful thing and those who don't. Okay, anyway, that's what we'll do. And this is consistent with what we do for SL2R, at least. That's a virtue. No, that's certainly correct. That's a good point, except that at some point we'll probably integrate from minus infinity to infinity. So I was just more used. The answer is here, not no. Except for that fact, we will have other similar integrals later on. So in this case, now I have a Fourier transform, but it's not called the Fourier transform. Usually it's called the Mellin transform. We'll probably keep calling it the Fourier transform. But the point is that the character e to the itx corresponds to the absolute value of x to the it in multiplication. So this is what happens on R, and this is the corresponding thing which happens on R positive. As he just pointed out, there's no reason for the absolute value except that sooner or later we'll look at the full multiplicative group where sign counts. And so the Fourier transform becomes something called the Mellin transform. So I have f hat of s, and furthermore, the Mellin transform has another thing. It shifts this to this. So now s is in it. It's an imaginary point. So I have the Mellin transform as f hat of s is equal to the integral 0 infinity of f of x against x to the minus s dx over x. Again, the multiplicatively invariant measure is this, in the sense in which dx over x is equal to cx over cx, because the c's cancel. So this is the multiplicatively invariant measure on the positive reals. And so my Fourier transform becomes this, and as I say, there's a shift where s is now usually almost always taken to be an IR. That's actually, in some sense, the more natural choice anyway, even for the additive group. Okay. And so the Fourier transform says that the rapidly decreasing functions on the positive reals is isomorphic now to the short space of the imaginary axis. So all I'm doing here is just changing coordinates, taking logs and exponentials back and forth. This is just a repeat statement of what happened before. Are there any questions? Okay. So this, as I say, will be consistent with what we do for SL2R. Now, there's another space, and this is my idiosyncratic belief that this is an interesting space. Analysts don't like this because it's the most trivial space you can possibly imagine from an analytic standpoint. Let's look at what this space is. So this is where my notes become incomplete. There's no more on my notes, so I have to tell you. So I take the positive reals, and these are the intervals 0 to infinity. And I define now S of R. It's a different short space. I define this, actually my other thing, I call that the Harish-Chandra short space for reasons somebody will explain. So this is what I call the real short space, and there's some reason for this. These are functions in the short space of R such that f is identically equal to 0 on minus infinity 0. So a function in this short space is, well, it vanishes at 0 identically, and it's rapidly decreasing over here. So it's 1 over xn here as x goes to infinity. Here, at 0, it's Taylor series at 0, and what that means is that it's Oxn, and this is all in. It's Oxn as x goes to 0, all n. So these are stronger conditions. So the short space, this short space, this is included in this short space. Excuse me, the other way around. This short space is stronger. Vanishing of order x is stronger than vanishing of order log x. And so this short space is included in the previous one. Yeah? F. There should be an F there, but that's all right. What is your? Functions on all of R when extended by 0, right? So in particular, so here's the thing. They're 0, so they're 0 identically here. That means, and they're smooth, which means that their Taylor series is 0, identically 0 here, because the Taylor series is certainly the same from left and right. So all their derivatives vanish from the left side. That means all the derivatives vanish from the right side, and that means that they're of order Ox to the n for all x, again by the theory of Taylor series.
I just think the objection is that
I'm sorry, what are you saying, Peter?
I think the objection is that in the first sentence, you don't put a condition on it at infinity. But you do in the
Oh, I'm sorry. Oh, Schwartz, yeah, it should be Schwartz functions. It should be, there should be the word Schwartz should be in between there and there. Absolutely, yeah, they're in the Schwartz space of R. That's right. Okay. And now, this might, now, I'll say, well, I won't say much more about this, as I say, but there's a reason, the reason for introducing this space is that it's the smallest space on which the Mellin transform becomes holomorphic. So, and the CC infinity functions, let me add the following. So we have three spaces, they're somewhat related. Included in this are the CC infinity functions from 0 to infinity. So it's a little thing that looks like that in increasingly strict conditions. And the CC infinity functions are used most often by analysts. They're an interesting space. But in global analysis, somehow it's the other space which matters. And the point is that if f is in the Schwartz space of 0 to infinity, then f hat of s, which is equal to the integral 0 to infinity of x to the minus s f of x dx over x, this is defined and holomorphic for all s. Analytic, complex analytic. For all s and c. And this is the smallest space with that property. So usually what happens is people take functions of compact support, and then, again, this is certainly correct. That's one space is included in mine, so this is still analytic. And there's some very nice condition. There's a kind of a Paley-Wiener theorem which characterizes these, which I won't state. We may state it later. Well, we probably will state it later. Okay, and so the point of S of S. So I'll also call this S of 0 to infinity, is that it is the smallest space for which this is true. For S and all its derivatives. I'm sorry, I heard somebody say something, yes?
Is it the largest space that
It's the smallest space for which the Mellin transform is holomorphic. If you impose the condition that all the derivatives also have Mellin transform, which is
but
holomorphic.
0 is even smaller?
No, it's it's the largest space. Yes, sorry. Yes. Yes. Right. Thank you. Thank you. Okay. A few typos again. There's a connection which we'll need, but I won't need it until my talk on Selberg trace. Actually, I'm done. Are there any questions? I'm embarrassed that I'm done so quickly. Yes. CC infinity. I'm sorry. This means smooth functions of compact support. In general, if I have any manifold whatsoever, this is CC infinity of M with smooth functions of compact support. Okay. So, for example, if I take a function which is of compact support, and then again, because it's rapidly decreasing, its Mellin transform will be holomorphic everywhere in S, and there's some classical theorem due to Norbert Wiener and Arthur Paley that characterizes those functions. It's even easier to characterize by these Fourier transforms the functions which lie in this space. That plays a role in Fourier analysis on SL2R through some work of Arthur's. Okay. Yeah? Well, from an analytical standpoint, it's really a very simple space. I'll tell you how to characterize the Fourier transform. So, Paley-Wiener theorem for compactly supported functions is rather difficult. There's some tricky things to verify. It's not terribly hard, but there are some tricky points, and even the statement is a bit messy. Right, that's right. So the classical, I'll write it down. The classical Paley-Wiener theorem there are many classical Paley-Wiener theorems, but what's used most often in modern terms tells you which analytic functions, which entire functions, entire being analytic everywhere, are the Fourier, or the Mellin transforms, well, are the Fourier, the Mellin transforms of CC infinity of 0 infinity. And this is somewhat tricky, not terribly hard, but. And there's the characterization, so there's a similar theorem for the Schwartz space. Similar, but much more trivial theorem. In fact, there are dozens of Paley-Wiener theorems characterizing all different kinds of growth conditions. So, for example, there's another theorem characterizing L2 functions of compact support and so on. So there's a whole family of Paley-Wiener theorems, which is why it's fair to call this one. So characterizing, well, describing exactly the Mellin transforms of F a member of the Schwartz space. And this is very simple. So here's my line IR. Here's the complex plane. And the characterization is that F of S equals O of 1 over 1 plus the absolute value of the imaginary part of S to the n, minus n, no, n, unbounded vertical strips. So if I take a bounded strip, so we know that if I take the Fourier transform itself, then it's rapidly decreasing on this single line, but now the functions in this space are just rapidly, I have the same rapid decrease condition, but it holds true on bounded vertical strips. It's easy enough to show. You do that by moving contours around. Almost all Paley-Wiener theorems involve moving contours around in some way or another. This one's the simplest of all.
Why do you need the 1 plus? Why do you need the 1 plus?
Oh, because if I put in, it's 0.
Yes, but still, there's only a decrease condition at infinity. You don't have
Anyway, it's normal to do that just to eliminate the problem of dividing by 0.
You didn't do that for x.
Yeah, but I carefully said as x goes to infinity. Okay, here it's a little more complicated because I want a single constant to work for all, but so I didn't. It's a more precise statement. Okay, and there's a very similar theorem. So in the theory of SL2R, so what's going to happen is, what you're going to see is that there's some kind of, almost everything I've said here applies to SL2R. I have a notion of CC infinity of SL2R, so I have all the same spaces. So I won't tell you what those spaces are except for the obvious ones. But this is exactly the same filtration. I have CC infinity of SL2R. Those are smooth functions of compact support. Then I have my Schwartz space of SL2R. Then I have something called the Harish-Chandra-Schwartz space of SL2R. Okay, then I have L2 of SL2R. Then I have the duals. So I have the dual of this. These are tempered distributions in the Harish-Chandra sense. I have this space, S prime. Then I have CC infinity of prime. And so I have, this is contained in this, contained in this, contained in this. This is, I can integrate something in here against something here. So this is contained in here and so on. So this is contained. So I have this whole filtration of 7 different spaces corresponding to what I have for the multiplicative group as well. And each one of these spaces plays an interesting and important role in the subject. It's just more technical to explain what these spaces are because SL2R is a more complicated group. And for understanding applications, understanding all these spaces is fairly important. Okay, now I really am through, I think. Yeah. What do I call it the Harish-Chandra, everybody calls it. It's the Harish-Chandra Schwartz space. Okay, Dragan, I think you're going to explain that today, are you? That's right. So the whole point of my talk was to set you up for the more complicated, so to give you sort of some familiar analogs and to set you up for what happens for SL2, so you get some intuitive feel for these spaces. Yep. Any other questions? No. Okay, I'm through. So I'll post these notes when they're more complete, but that's about it.